There are two competing theories about the origin of the universe. Okay, I'm only going to show you one of them. Okay, the other competing theories. So there's the Big Bang, and by the way, the Big Bang was meant as an insult. It was meant to discredit some guy. I think Arthur Hoyle is the guy's name. He was an astronomer. He really hated the Big Bang model, so he called it the Big Bang, and thinking that it would discredit it. And of course, ironically, and this is true irony, he actually gave it a name that stuck, that everybody could understand. Okay, but the Big Bang is the notion that the universe emerged from a singularity 13.7 billion years ago, plus or minus 0.2 billion years, okay, and has been cooling ever since. It started out hot and is now cool. And the main reason we originally started to think this was that we observed the expansion of the universe, right? So this is a main reason. The other competing theory is Chris Murrayism, okay, which states that the universe was created by Fiat, an Italian auto manufacturer, okay, on the morning of November 1st, 1962, right? And I know your parents will say, some of them will say, well, I was born before that and I remember that, so therefore that's false. But no, they were created at whatever age they were at that time with memories, right? All of the cosmic microwave background radiation, all of these galaxies that we so-called see, right? Okay, we're really not seeing. All the light from those galaxies was created en route to us with all of the fossil evidence of dinosaurs, all this stuff, right? The universe is actually quite young, I think. Okay, but I won't really go into that theory. I'm just going to more go into, I'm going to go into a theory that's supported by scientific facts. Okay, I know it's a sad thing, right? It's also called the Standard Model, and for various reasons, okay, it really is the only thing there. I mean, you might hear like the Big Bang Theory is in trouble. It's not really. Okay, so it's you know, you could argue about, you know, what happened before the Big Bang and all this stuff, right? But there's tons and tons of evidence that the universe emerged from a big fiery singularity 13.7 billion years ago, and that's where we're headed today. Okay. So these are precepts. Basically, precepts are just things that we generally hold to be true, and if they're not true, then we just don't want to play the game. We don't want to, you know, we're out of there. If any one of these things, you know, is not true. The first one is that the laws of physics are the same throughout the universe. And I'm getting these, by the way, from the Timothy Ferris book, The Whole Shebang, which I highly recommend. And he may have even written a more updated version of it, but it's Timothy Ferris. Okay, and it's The Whole Shebang. And it's you know, I think it was current in 1997. He may have written a new version of it. I don't know. Okay, but these are the precepts. The first one is that, like, the laws of physics. So, for example, the speed of light. If I look halfway across the universe, over there, the speed of light's the same as it is here. Okay, hydrogen atoms have the same spectral lines as they have here. Yeah. Okay, the universe is expanding, and it's pretty hard to argue with this. Okay. The universe is isotropic and homogeneous. Homogeneous, let's talk about ice cream. Okay, let's talk about ice cream and an ice cream with pecans in it or something like that, right? If you've got ice cream with pecans in it, the notion of homogeneous means that the pecans are not all in one little clump at this side of the ice cream. You know what I'm saying? If we scoop a scoop of a certain size out of that ice cream, we'll always get the same number of pecans. Okay. Isotropic means that there's no trend, that the universe, all the pecans aren't in the upper layers, and as you go down, there's no trend toward fewer pecans or something like that, right? Okay. Now, what's interesting is that this one is not challenged. There's no trend. We don't go farther away and we see, you know, more galaxies or fewer or something like that, right? But homogeneous is pretty hard to argue this one. Okay. Sometimes where we've got problems with that, go ahead and do what you need to do. Because the scoop keeps getting bigger and bigger. There's lots of large-scale structure, and we have no idea why that is. So our ice cream scoop keeps needing to be really, really big, right? Clearly the scoop is bigger than a galaxy, right? Way bigger than a galaxy, because you could scoop galaxy and then there's lots of space where there's no galaxy, right? So it's, you know, it's some intergalactic distance, large intergalactic distance, and it keeps getting bigger. So, what? Yeah, we're talking megaparsecs, maybe. Mega! I'm like a jukebox. Mega, mega. Okay. We think general relativity works in the big scale things. We're away from a singularity, it works, right? If it doesn't. And then the early universe is hotter than it is today. And this is something we learned in Physics 1, is that adiabatic expansion causes things to cool, right? Now, literally, the universe cools. When we talk about cooling, we're specifically talking about the photons, the primeval photons that emerge from the Big Bang. Since the whole universe has gotten bigger, these photons have stretched. And when photons stretch, what happens to their energy? Large wavelengths have less energy, right? So this is a fundamental concept. E is hc over lambda. If the universe stretches, lambda stretches, right? Because light travels through space itself, and as space itself stretches, right? As space itself stretches, then the wavelengths of light traveling through that space stretch, the energy decreases. The energy per photon is a measure of the temperature, okay? So yeah, this is this, right? The universe is evolving. By this we mean things like quasars. Back in the origin of the universe, quasars were bright because there was lots to eat. Now they're not as bright because there's not as much to eat. Quasars are these giant black holes devouring matter, right? Okay. Back in the early universe, there were more spiral galaxies. Now there's more elliptical ones because collisions create elliptical galaxies, right? There are certain trends like that, right? Okay. And then this is a very important one, the cosmological principle. Okay. The cosmological principle states that if your theory works, only if you are in a special place or special time, it's not likely to be the correct theory for the universe, right? And the biggest violation of this was, of course, Ptolemy's model of stars and sun. Yes, what was this model? The Earth sits still and is this, immovable thing, right? Okay, and all the planets and all the stars and the sun move at astonishingly fast rates around it. Yes, this is one of the problems, was how fast the stars would have to move to go all the way around. They knew the speed of light roughly, and they knew that that was a problem, right? Okay, so this is a very important thing that we'll go back to later. Okay, so these are our precepts. We think these are all true, right? So let's just do a little bit of history. Okay, relativity predicts that the universe expands or contracts. Hubble discovers that it expands. And in the 1940s, Gamow was one of these scientists that worked with Niels Bohr at the Quantum Institute, and he was the cartoonist. You can go and look at Gamow cartoons. He drew like cartoons of Schrodinger's cat and all this stuff, and was apparently a real character, right? So Gamow is working with some other people, and they're working on the Big Bang model, and this is when it got its name, I believe, is back then. And this is the notion. It's just that if we see the universe expanding now, doesn't that mean it was smaller before than it is now? And if we go back far enough, we can project this to a singularity. We can actually project the universe down to a singularity. If you go back far enough in time, you ought to get to like 1 point, right? Okay. And if it was once small, it once was hotter than it is now. Well, how hot? Well, the sky's the limit. Okay. It's from the singularity to now, the singularity was incredibly hot. Okay. It was so hot that photons, ordinary garden variety photons flying along, could create Higgs bosons and all sorts of exotic particles, right? So this is how particle accelerators are time machines. In the early universe, photons of sufficient energy could create massive particles like the Higgs boson. And now, to create one of those, you've got to have this underground particle accelerator. And what they do when they make these collisions is they create a little miniature Big Bang. They create particles that haven't been around for a long time because there's not enough energy today to make them in general. What? The Higgs boson is this super giant. It's like I think it's tera electron volts of energy, right? We're like a proton. To make a proton, you need like a giga electron volt, right? 938 million electron volts is the rest mass. This is like this super giant thing, right? It's like thousands of. It might not be a tera, but it's like giga, right? Okay, so that's the notion. And then before we get any farther, let's all dispel. There's certain common misconceptions, right? And the first one is that the Big Bang happened over there, and matter flew through space that already existed. What you need to know is that space itself was created.